Hello, good afternoon to you all my viewers. Today again I have come to do a video recording on kinetics of second order reactions part 3, an alternative easy and alternative approach which rather than I have done in lecture L07. This is a rather easy way to formulate the integrated rate equations and other features like say how to determine the rate constant of this reaction, a suitable example of this reaction, and half-life period of this reaction, and if one reactant have taken in excess between the two reactants, when the two reactants initial concentration of the two reactants are not equal, then if we take one reactant in excess, this reaction the second order reaction turns the first order kinetics, and so this is why it is also called pseudo unimolecular reaction. Then lastly, how this integrated rate equations of these two substances with unequal concentration can be used to formulate the integrated rate equation for the two reactants having the same initial concentrations. These are the items, these are the features I shall discuss today as far as it is practicable for me, as it is possible for me. So let us start the reaction A plus B and giving you the product P and product P. So let the initial concentration of A is not equal to the initial concentration of B. Means two different substances are reacting with unequal concentrations at the start of this reaction, and let at t equal to 0, thus initial state, thus the initial time it is the concentration of A0 and it is the concentration of B0 and P equal to 0. This third bracket indicates the molar concentration of these respective substances, and these two A0 and B0 are known to us while we are doing this experiment, and these two are the initial concentrations of these two reactants, and these two concentrations are not equal. So let and after time t, this concentration of A is third bracket A, molar concentration of A, and it is molar concentration of B, and let x mole per liter of A is reacting after time t. So concentration of A equal to concentration of A0 minus x, or you can say A minus x if A0 is taken as A and B naught is taken as B. It is more better to write A and B. These two are the initial concentrations of these reactants and these are not equal for this type of reactions. So, concentration of B is also concentration of B naught minus X equal to B minus X. So, these are the simple to write, and since A and B are reacting 1:1 mole, so X mole of A reacts with X mole of B to give this product. So, concentration of A remaining after time t will be equal to A minus X, and concentration of B after time t will be B minus X remaining in this reaction vessel after the time t. So, the rate equation, differential rate equation, rate equation of this reaction is d concentration of A minus by dt equal to concentration K2 and concentration of A and concentration of B. K2 is the rate constant, and you know this K2 is the rate constant of this reaction, and which is very important term of this reaction. If you know this K2, then variety type of parameters of this reaction you could calculate easily. But concentration of A equal to A minus X, so minus d concentration of A by dt equal to d A minus X divided by dt, and this is equal to d minus equal to minus d A by dt and plus dx by dt, and this is equal to dx by dt, as this first term is equal to 0. A is initial concentration and it will not vary with this time of this reaction. So, this rate of this reaction, differential rate, we can write dx by dt equal to K2 into, instead of A we can write A minus X, and instead of B we can write B minus X. So, this is the differential form of this rate equation in terms of A and B and X. So, this is equation number 1. Dx by dt equal to K2 A minus X into B minus X, and this one we can write this one equation. This is equation 1. This is equation 1. Now, the different parameters, first we formulate the integrated form. Integrated form of the rate equation. This is the feature number 1. So this differential rate equation could be integrated. First we shall have to separating the variables dx divided by a minus x into b minus x equal to k2 into dt. So this integration is not easy. Now integrating integration dx divided by a minus x into b minus x equal to k2 is the time independent constant, so integration of this dt. But this term we can split up or we can write 1 by a minus b and integration dx into b minus x minus integration dx by a minus x, third bracket close, equal to k2 into integration dt. Now we are doing the definite integral. So if we split up this term in this fashion, then you can see dx common, and here a minus x minus b plus x will be cancelled, and so it will be a minus b here, and this is divided by a minus b. So or we can write 1 by a minus b, and here integration minus ln b minus x, and here plus ln a minus x, third bracket close, k2 into t plus some constant ic, integration constant. So if we rearrange, then a by a minus 1 by a minus b, and here ln, this will come up according to the law of this logarithm. Here b minus x will be at a denominator and equal to k2 t plus ic. So to determine the value of ic, we have to put some boundary condition, and this boundary condition is that here the most suitable boundary condition is that when time t equal to 0, x equal to 0. So when t equal to 0, x equal to 0, putting here 1 by a minus b and ln, then a by b equal to t equal to 0. So this term is 0 equal to ic. Putting this value here, we have 1 by a minus b ln a minus x divided by b and b minus x equal to k2t plus 1 by a minus b into ln a by b. So by multiplying A by B, we have ln A minus x divided by B minus x equal to K2 into A minus B and T and plus ln A by B. So this is one of the integrated form. We can write here ln A minus x divided by B minus x equal to K2 into A minus B plus ln A by B. This is equation number, say, 2. However, if we bring this term here left hand side, then it becomes ln B into A minus x A into B minus x equal to K2 into A minus B into T. This is also another form of this integrated equation. So we can write here the ln B into A minus x, here A into B minus x equal to K2 into A minus B into T, and equation number 3. These two are the integrated form. These two are the integrated form of this rate equation. Next, second feature. So we have got this integrated form of this rate equation for this second order reaction when the two substances have different initial concentrations. Now the evaluation of K2, K2 the rate constant of this reaction, which is a very important parameter of this reaction, and how by graphical method we shall have to do some experiment. We here the variables are only x and t, here x and t. Here the variables are only x and t. So if this equation 2 can be plotted here time the independent variables, here it is ln A minus x divided by B minus x, it is the dependent variable. Whenever plotted according to this, according to the equation 2, it will be y equal to mx plus c. So it will be like this. So this intercept, here it is time t equal to 0. So intercept is equal to ln A by B, and slope will be equal to K2 into A minus B. Since initial concentrations of A and B are known to us while we are doing this reaction mixture, so K2 could be determined from this plot by graphical method. Or equation 3 could also be plotted. Equation 3 could also be used. Here t equal to 0 here, and in this case ln B into A minus x divided by A into B minus x plotted along this y axis. So it is the y equal to y equal to mx. So, straight line passing through this origin, and slope will be equal to k2 into a minus b. So, from this slope also k2 could be determined, as a and b of these two substances are known to us. This one equal to a and this one equal to b. Now, the third feature, one example. Best example often used in chemistry honors courses, the example saponification reaction. Example saponification reaction. Or alkaline hydrolysis of ester. Alkaline hydrolysis of ester. So, it is, say, ester is CH3, C double ethyl acetate, aqueous, plus sodium hydroxide, aqueous, and giving this sodium acetate plus alcohol. All are in aqueous. It is also aqueous. So, initial concentration of these two reactants have been taken, and these are known to us in a reaction mixture, and among the two, sodium hydroxide is easy. Concentration of sodium hydroxide could be easily determined by titrating with standard oxalic acid using this phenolphthalein indicator, and so some adequate amount of this reaction mixture has been withdrawn from this reaction mixture, and it is actually the reaction is stopped by adding it in dilute in water, in ice cold water. So, reaction at low temperature and with the dilution reaction is freeze, and so it is then titrated with oxalic acid, and the value of B minus X is determined. Since B is known, so X could be known. So, we can do one table, here X, here T, and here X. T equal to 0, X equal to 0, T equal to T1, it is X1, T equal to 2, T2, here X2, and T3, and here X3. So, X is known, AB are known, X is known at different time intervals, A and B, these are knowns. So, by plotting we can get this value of K2 of this saponification reactions. Actually, this is the way by which these soaps are prepared from this glycerides of long chain fatty acids with sodium hydroxide, and this is why it is called the saponification reaction. Now, we are coming to the fourth feature of this second order kinetics, when this concentration of the reactants are not equal, and this fourth feature is the half-life period. This type of reactions have as such no half-life periods, but we can calculate the half-life periods either with respect to A or with respect to B. Say with respect to T half with respect to A. So when in this condition, when T equal to T half, A equal to the initial concentration of A, X equal to A by 2. The half of this A has been reacting within this time T half. So putting in this equation 2, we have ln A minus, instead of X will be A by 2 and divided by B minus A by 2. Or better, we can use this equation number 3. That will be good. ln B into A minus A by 2 and divided by A minus A into B minus A by 2 equal to K2 into A minus B into T half. So if we T half will be equal to 1 by K2 into A minus B and T half 1 by K2 A minus B into this one is ln B into A by 2 divided by A into twice B minus A by 2. So A cancels, 1 by half cancels, so it becomes T half with respect to A equal to 1 by K2 into A minus B and ln B by twice B minus A. This will be the half-life period with respect to A. This will be the half-life period with respect to A. So similarly, whenever we try to calculate the half-life period with respect to B, then when T equal to T by half, X equal to B by 2, or half of this reactant B is depleted by this reaction. Then here putting again using this equation number 3, then ln B minus B into A minus X equal to B by 2 and divided by A into B minus B by 2 equal to K2 A minus B into T half. Or you can write T half equal to 1 by K2 into A minus B, K2 into A minus B into ln, here B into twice A minus B by 2 and divide by here A into B by 2. B cancelled, half cancelled. So T half equal to 1 by K2 into A minus B into ln 2A minus B divided by A. So T half with respect to B equal to 1 by K2 into A minus B into ln 2A minus B to A minus B and divide by A. So since we know A and B, the initial concentrations of this reactant A and B, K2 is also known for this reaction, then it is possible to calculate the half-life period with either with respect to A or with respect to B. Then fifth feature. Fifth feature, this whatever among these two reactants, if we take one of the reactant in excess, then half-life period, then rate of this reaction does not depend on the concentration of this reactant which has been taken in excess. So this second order reaction becomes the first order with respect to A, which is taken in a very small amount in this reaction vessel. So this reaction is called the pseudo unimolecular reaction. So pseudo unimolecular reaction. Pseudo means pretended. It is actually two molecules, two reactants are participating, but still it is behaving the first order. So we as if the reaction is pretending to be the first order. So we can use this equation 1, equation 3. Let B is greater than A. B reactant taken, initial concentration of B taken in excess in this reaction vessel with which is reacting with the A which is taken in smaller amount. Then equation 3, if we put, then actually A minus B almost equal to minus B. A minus B almost equal to minus B. A is very small in comparison to B. And then this one actually B again, B is much greater than X. So X you could neglect in comparison to B. So putting here this ln b into a minus x and divide by a into b. X is neglected, which is very small in comparison to b, and in right hand side k2 into minus b at t. So if we bring this minus here and b cancels, so if we take this minus in the left hand side, then according to the laws of logarithm, this will upside down. So it will be ln a divided by a minus x, and this is equal to k2 into b and t. Or you can write b is constant, k2 is also constant, so multiplication of the two will give you a new constant, and here you can write this ln 1, this term we can write ln a by a minus x in equal to k1t, where k1 equal to k2b. So this is actually the first order kinetics. This is actually first order kinetics. So second order reaction, where two reactants are participating, still it behaves or it follows the first order kinetics. So this is why first order kinetics means for the elementary reaction it is unimolecular reaction. So this second order or bimolecular reactions pretending to be a unimolecular reactions, and this is why it is called pseudo unimolecular reaction. Pseudo means pretended. Then last one, then sixth features. Then sixth features, the then sixth features, this third equation 3, sixth features, this equation 3 integrated form is not valid when A and B are equal. If we take these two initial concentrations of this reactants are same, then this equation is not valid. A equal to B means this term equal to 0, then right hand side becomes 0, this equation will vanish. So, but by using some short mathematical tricks, it is possible to transform this equation into the integrated form of this equation when both these reactants initial concentrations are same. How it could be done? Let us equation 3. Equation 3, ln b into divided by a into b minus x equal to k2 into a minus b into t. We have to transform this equation into the form 1 by a minus x equal to K2T plus 1 by A. When both these reactants are same, both the reactants are having the same concentration or identical, then in this case this integrated form of this equation is like this. So we have to transform this equation to this one by some mathematical tricks. How could we do it? So here we can write ln 1 plus say suppose P divided by A into B minus X, third bracket close, equal to K2 A minus B into T. Now what will be the value of P? Actually 1 plus P divided by A into B minus X, we are writing this one instead of this. So it is equal to B into A minus X into A into B minus X. We are trying to find out the value of P which will be put here. So or A into B minus X plus P, here A into B minus X equal to B into A minus X divided by A into B minus X. So this term cancels, or we can write AB minus AX plus P equal to AB minus BX, or P equal to AB cancels. So P equal to this term will go right hand side, it becomes plus. So A minus B into X. So instead of P, we can write ln 1 plus A minus B into X divided by this one A into B minus X, bracket close, equal to K2 into A minus B into T. Now we can remove this term. We have already got this value of P. Now you know, according to the logarithmic, ln 1 plus x almost equal to x when x is much less than 1. So instead, in this case, A and B are equal, or almost equal. A almost equal to B, so this term vanishes to, this term almost reduced to 0. So when this term is very small, this whole term becomes much less than 1. So we can also write here this A minus B into X divided by A into B minus X equal to K2 into A minus B into T. So A minus B cancels. So this equation turns x by A into B minus X equal to K2T, or this term can be split up. It is 1 by a minus x, we can write minus 1 by a, then a here coming, here minus a plus x, so this term is coming equal to k to t, or 1 by a minus x equal to k to t, and this term if we transform to the right hand side, then this. So this equation turns into this equation, this integrated form whenever both these reactants having different initial concentrations now turns into this one when the two reactants having the same concentrations by using this equation 3 and putting this logarithmic tricks. So this is all about the second order kinetics of second order reaction. It is given part 3, an easy alternative approach, and in my next class I shall try to get this integrated form of this nth order reactions, and from this nth order reactions we can get any order, first order, zero order, first order, second order, third order, or fraction order, any type of kinetics of any order of this reaction could be derived from this expression of integrated form of this nth order reactions. So thank you all for watching my video, and I hope this video you can grasp it, you can understand very easily instead of the previous one.